In this video, we're going to talk about acid-base reactions, also called the neutralization reactions. Before we actually go ahead and write down the acid-base reaction, it's important to know the definition of an acid and a base. And in this particular lecture, we're just going to be only focusing on the Arrhenius-based definitions of acid and bases. There are actually two other ways of defining acids, one of them called the Bronston-Lowry and the Lewis acid-base definitions. But here we'll just focus on the Arrhenius concept of acid and bases. And according to Arrhenius, acid is going to be any chemical that's going to be giving out H plus in aqueous solution. So all the oxyacids and binary acids that we have talked about are actually Arrhenius acids. So for example, the HF, which is hydrofluoric acid, hydrochloric acid, HCl, hydroiodic acid, those are some of the binary acids. And if I write down some of the oxyacids, that's going to be HNO3, you have H2SO4, that's sulfuric acid. I can write down H3PO4, that's phosphoric acid. So those are your oxyacids, and they're also going to be the Arrhenius acids. And make sure you know your 6 strong acids from the list of the Arrhenius acids. So your 6 strong acids, out of 6 of them, 3 of them are binary acid. That's going to be HCl, that's hydrochloric acid, hydroiodic acid, and hydrobromic acid. And then you have 3 oxyacids that are considered to be the strong, HNO3, that's nitric acid, sulfuric acid, and then perchloric acid, HClO4. All right, so then as far as the base go, the base is going to be any chemical that gives an OH minus. If you guys recall what's an OH minus, it's an hydroxide. So any chemical that can give a hydroxide in aqueous solution is going to be in a base. And for the most part, we talk about here the metal hydroxides. And some of the strong bases that you're going to be seeing are coming from alkali metals. For example, LiOH, that's lithium hydroxide, or KOH, that's potassium hydroxide, or I have NaOH, that's sodium hydroxide, all the way to rubidium and francium hydroxide. So these are going to be all alkali metals hydroxides. In addition to that, you can also have the second group metal hydroxides, for example, calcium hydroxide or strontium hydroxide or even barium hydroxide. Okay, the calcium hydroxide and strontium hydroxide, they do have some solubility issues. They don't really dissolve much in water, but whatever amount of strontium hydroxide or calcium hydroxide is dissolved is still considered a strong base. Okay, so that's your definition of the base. So like keep in mind, acid gives the H plus and the base gives the OH minus. So that's the simplest definitions of the acid and bases. So now let's talk about the reactions of an acid and base. So anytime we have an acid reacting with a base, one of your product is always going to be water. So you can always start out predicting the products of acid-base reaction by writing first the water, and then the other product is going to be the salt, and the salt is dependent on what type of acid and base you're really using in that case. Okay, and sometimes you also produce carbon dioxide depending on if you're using like carbonic acid and stuff like those. Let me give you a simple example. If I have NaOH plus HCl, so first of all, you want to be able to figure out what's the acid and what's the base in this reaction based on the definitions. So remember HCl, it's a hydrochloric acid, so that's going to be your acid here, and NaOH is going to be your base here. You got the OH or the alkali metal in there, so that's going to be the base. And we said one of the product is always going to be the water, so you can go ahead and write down the water. And the way you really look at how the water is made, you bring in the OH from the base and you bring in the H plus from the acid, and they get combined together to make a water. So that's how you make water in there. Now what's left behind is going to get together to make the salt. And this is where you have to be a little bit careful with the formula of the salt. Now in NaOH, what's the charge on Na here? Well, Na is a 1 plus. I'll write that on the side here. And what's the charge on Cl in HCl? Or what's the charge on Cl in ionic compound to begin with? It's always going to be Cl minus. So when you're putting it together, it's going to be one of the sodium and one of the chlorides that will balance out these charges. It's just going to be an NaCl. So everything here is usually written as an aqueous form, which means it dissolves in water. So NaOH aqueous and HCl aqueous, and NaOH is aqueous, HCl is aqueous, and the salt that we make, NaCl, is also going to be aqueous because remember the solubility rules, it dissolves in water. And then the water that's made is going to be a liquid. You don't write that as an aqueous. Okay, so usually the formation of the water is the driving force for these acid-base reactions, and all these acid-base reactions are all highly exothermic. They produce a lot of energy. So if you mix an acid and base in a container, you may see or you may feel that the container has been warmed up because it's releasing a lot of heat. Well, let me take another example and and where it may not be one-to-one. So in this particular example that we just took, the NaOH and HCl, they have one in front of each other as a coefficient because this reaction was already balanced to begin with. So this is called a one-to-one stoichiometry relation between the acid and base. Now you don't necessarily have to have only one-to-one stoichiometry relation between the acid and the base. You could have 1 to 2 or 2 to 1 or 1 to 3 or anything like that. So let me take an example where you see in a different stoichiometry relation. Assume I have barium hydroxide and I'm reacting that with HNO3. So like I said, again, you want to be able to figure out what the acid here is and what the base here are going to be. So barium hydroxide is going to be your base, and HNO3 is one of the strongest acid we got there, is the nitric acid. Okay, so then when they get combined together, obviously they're going to make water. So like we have said, one of the product is always going to be water. And if you look at how the water is made, you can again see, okay, the hydrogen and the hydrogen from the acid and then the OH from the base is going to get combined to make water here. And then it may not be balanced momentarily, but don't worry about that. The first you have to actually predict the products. So then what's left behind? In barium hydroxide, what's the charge on barium? Well, if I write that down on the side here, barium is actually 2 plus, and what's the charge on NO3? NO3 is one of the polyatomic anions that you guys had to memorize. It's NO3 1 minus, so when you're putting those together, what should be the formula? Well, I would need two NO3 1 minuses to balance out the 2 plus charge, so the formula is going to be BaNO3 2 minus. Okay, so everything is still going to be in the aqueous form except the water, which is going to be in the liquid form. All right, so then remember to figure out the correct formula of the salt. And once you have the correct formula of the salt and your water written out, you want to go ahead and balance out your reaction. So when you're balancing out your reaction, you can clearly see I have two nitrates on the product side, but I have only one nitrate in nitric acid on the reactant side. So maybe I can go ahead and put 2 here in front of the HNO3, and that takes care of the nitrates. And then you also want to look at the hydrogens. When you look at the hydrogens, you have 4 hydrogens on the reactant sides because you got 2 coming from the barium hydroxide and 2 coming from the nitric acid since you put 2 in front of the HNO3. So right now you have only 2 hydrogens in the water. So what you want to do, you want to put 2 in front of the water, and that takes care of the hydrogens. And you can clearly see the oxygens are also balanced out when you put 2 in front of the water. So now this particular reaction is actually a 1 to 2 mole ratio. When you look at the acid and the base, there is 1 in front of the base and 2 in front of the acid in the stoichiometry relation. So it's a 1 to 2 mole ratio. And that also explains because 1 barium hydroxide actually producing two OH minus ions in there. So that's why it's a 1 to 2 mole ratios at the end of the day. Okay, so this is how you're going to be predicting the products of the neutralization reactions. Okay, a typical question in a neutralization reaction involves a titration of an acid within a base and vice versa. And there are going to be times when you're given the information about one chemical, either the acid or the base, and you have to figure out the information about the second chemical. Okay, so let's look at this particular question here. It says a student titrates 50 milliliters of acetic acid with 0.45 molar NaOH, and if 75 milliliters of NaOH is required to neutralize the acetic acid, calculate the concentration of acetic acid. So in chemistry, when they say concentration, most likely they're talking about the molarity. So it's an uppercase M there. And if I look, the information I have, we're given the acetic acid, all right, and we're given the NaOH. Well, first of all, you may want to rethink and look up what the formula going to be for acetic acid. Acetic acid, since it ends with ic acid, it's coming from an acetate ion, and acetate ion is CH3COO minus. So your acetic acid is going to be CH3COOH, all right? And that's one of the oxy acids as well. Then plus you have NaOH. And before you actually start doing the problem, you must write the balanced equation. Now, there are going to be times when you're given the balanced equation, but then there are going to be times when you're asked to write down the balanced equation because you know what the product's going to be. One of them is going to be the water, and the other one is going to be the salt. Okay, so now let's see what the salt going to be. I got this hydrogen, so let me just use a different color here. I got this hydrogen and this OH taken out to make water, okay? And then you want to see what's left behind. What chemicals that we have left behind are anions and cation. In sodium hydroxide, we have Na+, and in acetic acid, we have this CH3COO minus left. So there's a 1 minus charge and 1 plus charge, so when you put them together, you would just need one of each. So it's just going to be CH3COO Na. Well, for the most part, the cation is usually written first before the anion, except in cases of these acetates, these carboxylates ions, when you actually write down your anion first and then you write down the cation. But even if you in Gen Chem, even if you write down your cation first and the anion, it's not going to be counted incorrectly. But when you take organic, you will be expected to write the anion first and the cations afterward. Okay, well, that's who your product's going to be, and then I can just go and write down this is going to be aqueous. That's also going to be aqueous. The water is going to be liquid, and sodium acetate is also going to be the aqueous. Okay, then we want to make sure the reaction is balanced. Seems like everything is balanced, so it's a 1-to-1 mole ratio. And this is a typical example of something a lot of time being done in the lab. So you titrate an acetic acid with a sodium hydroxide. So the information I have so far, I got 50 milliliters of acetic acid. I'm going to write that down here. So I got 50 milliliters of acetic acid, and I have 0.45 molar sodium hydroxide, and I'm told to neutralize all the acid by this base, we will be needing 75 milliliters of NaOH, and we have to figure out what the molarity going to be. So we're trying to figure out the molarity of this acid here. So we know the molarity of the base here, we know the volume of the base, and we also know the volume of the acid. Okay, so you can certainly use the stoichiometry relation and figure out what's the volume, what's the moles going to be for the acid, and once you know the moles of the acid, you can figure out the molarity, because remember, the uppercase M, which is the molarity, is literally the moles over liters. Okay, so since this is measured in liters, you want to make sure you convert your volumes into liters. So this 75 milliliters, quickly, how much is that going to be in liters? So you want to, at this point, you want to be able to quickly do these calculations to go from milliliters to liters, you divide it by 1,000, so it's going to be 0.075 liters. You want to do the same thing for the 50 milliliters, so you divide it by 1,000, so it's going to be 0.05 liters for the volume of acetic acid. So whenever you do these stoichiometry problems, whether it's just in a simple stoichiometry or a solution stoichiometry, or now in this case we're doing an acid-base stoichiometry, your central point has been always the moles. So you must calculate the moles of one reactant, and then you can figure out the moles of the other reactant, or you can figure out the moles of the product. We're gonna be doing exactly the same thing here. However, our starting points are different. Like in a typical stoichiometry question, you may be given the masses, and using the molar mass or atomic mass, you calculate the moles. But here, you're given the molarities. So if you're given the molarity and the volume, you can still use the definition of molarity and figure out what the mole's going to be here. Okay, so let's write that down. So I'm starting out with 0.075 liters of NaOH. Okay, and since I want to convert this to moles, and remember this 0.05, just 0.45 molarity can also be written as 0.45 moles divided by liters, because remember that's just the definition of molarity. I would have to put the moles on the top, so I'll put moles of NaOH on the top, and I will put the liters of NaOH on the bottom. And then after that, I just need to fill this number in. So this 0.45 goes with NaOH and 1 goes with the liters. So when you set it up like that, your liters of NaOH cancels out. Okay? Alright, so now you have moles of NaOH. So once you have the moles of NaOH, you can figure out the moles of acetic acid. And then this is where you're going to be using the stoichiometry relation. So I can write down moles of NaOH on the bottom and moles of the acetic acid on the top. All right, and then what number goes in front of the NaOH and CH3COH? Well, those are going to be your stoichiometry relation. So I have 1 in front of the NaOH and 1 in front of the CH3COOH. And that's why it's extremely important to balance your acid-base reaction. So if there was different numbers, that those numbers are the one that's going to be going at this point in this dimension analysis. But since this is 1-to-1 mole ratio, the life is a little bit easier here. So moles of NaOH cancels out, and that eventually gives you the moles of acetic acid. So if you want, you can go ahead and calculate the moles of acetic acid at this point, and then from there you can figure out what's going to be your molarity. So let's go ahead and do that real quick. So it's going to be 0.075 times 0.45, and that gives you 0.03375 moles of acetic acid. Okay, so now you know the moles of acetic acid, and we can easily calculate the molarity of acetic acid now. And that's going to be the moles, which is 0.03375 moles, divided by the volume of acetic acid is given to be 50 milliliters, and that's going to be 0.05 in liters. 0.05 liters. So all you really got to do is just divide that by 0.05, and that gives you 0.675 molar. So that's going to be the molarity of your acetic acid. So like I said, you could be given information about one chemical, like in this case you were given the information about the base, and you have to find the molarity of the acid, but you could be asked otherwise, where you would be given the information about the acid, and you could be asked to figure out the base. And the question could also be manipulated a little bit, where you could be given the concentrations and you may be given the volume of one of them, and you're asked to figure out the volume of the other chemical that's required to neutralize the acid-base reaction here. Okay, so hopefully this was a helpful video, and I'll have some more questions posted related to the stoichiometry. If you have any questions, leave the comments in the section.